Swayam Prabha. Digital India. Educated India.
Welcome back, participants. We are continuing with our session on product engineering and design thinking, and today the first lecture of module 7. The module 7 is on product complexity, affordability and design thinking, and this lecture is on tolerance design, which is based on Taguchi's robust design and engineering approach. As I indicated to you earlier, that this Taguchi method is a well known method, and there are several resources available, and in my last lecture, lecture number 30, I have provided certain links also for those. So, up to the parameter level design, there is not much difficulty because there are plenty of resources. You can go to any, there are many other materials, books also is there. So, whatever you intend to learn about this parameter design part, you can, and rather easily. But what I have observed, maybe you also will observe if you do some search, that the tolerance design practically has not been addressed. Practically, it is very scantily available, and therefore, how to proceed is not very clear to the users. So, I have taken that up as an exclusive lecture session, and therefore, today we will focus only on Taguchi's robust design methodology part, which is tolerance design. This is very important, particularly for complex products, where so many factors and components and variables are involved, and when the performance is being affected through by the variation in several inputs, and it is very difficult to decipher which one is that unless we have a systematic method like tolerance design, etc. Tolerance design is done only after parameter design, because once the parameter is decided, that is at what level the effect of these noises or the variations would be minimum, and then at that point also we need to optimize, in the sense that at a given point, say at a given temperature, say 50 degrees centigrade, whether it works best between 45 to 55 degrees centigrade or 48 to 52 degrees centigrade, that would give the best result. So, tolerance design becomes very important for that and at that level. So, product engineers, product developers, designers, they use this method, and so I am only trying to fill that gap, which is practically non-existent in as a tutorial video material, and would attempt to cover that. But let me tell you, I also have put a reference here when I chose an example. The example is not same, but a similar problem has been dealt with by Philip J. Ross in his book that I will discuss, but they are also certain results are placed, but the intermediate steps perhaps will not be so much detailed as you would see. Be that as it may, so I start from here with the short preamble stating that that our job is also to address this complexity of product, and that for that we need to discuss tolerance design. Hence, without further elaboration on this, I would like to go and go to the slide called concept covered. So, now here what I find is what you would see is that the focus is only on tolerance design, and we will discuss the approach, and this approach we would actually explicate with the help of an example problem, and then we would go to the steps. But of course, some of the steps are involved are part of, say, statistical methods, etc., where I have given the glimpse. But obviously, if you think that you need a little more learning on that, you can consult any book on say for example, ANOVA. ANOVA we have used, analysis of variance. So, you can use learn that from any such NPTEL, or say for any YouTube lecture, or say any online lecture, or say from books and etc. Those are easily available, but then I have just given the glimpse of it also, so that you know how to connect. But for obvious reason, because we are discussing product engineering, and hence we will not be able to go much into the details of all statistics, but these are simple steps and it is not very difficult for you to understand. However, I have placed it in very systematic stepwise method that will be rather convenient for you, I suppose. This already I have told you, but to start today's discussion, I am giving this reference once again that Taguchi proposed the robust design methodology, which starts with system design, and but Taguchi's major contribution is in parameter design and tolerance design. Here we have already discussed parameter design earlier. We will focus only on tolerance designs today. Here, as I said, it is presented with an example, and the preamble already are discussed in the last lecture. The there are various other aspects at the introductory stage, which has been discussed in lecture number 30. So, I would not repeat them here. If you want, you can go to my presentation lecture number 30 and find what was the content. It is the lecture number 31, just the previous one. Here I would just give you a glimpse of the tolerance design. As I said, it is a Taguchi based approach, but it actually works on the principle of standard deviation, or which normally we express as sigma, small sigma. Factors with a certain amount of variation about the nominal value, say a nominal value of a dimension, maybe say in millimeter, it is in and so what is the range? It will have a span, say range from minimum to maximum, as we see, as we know in a tolerance this thing. Now, to assess the effect of variance, it is not exactly the limit, or what is called that USL LSL, upper specification limit, lower specification limit based monitoring and tolerance stacking. It is not that, it is rather to check the effect of variance and of the inputs on the final product, the output, and here our purpose is to mitigate that by adjusting or tightening the tolerance more specifically. So, to what extent should we tighten? Should we and that rationality, because making it too close may increase the cost and demand on resources, which perhaps is not so much required. So, what is the optimal level? How much is we can tolerate. That is what we try to find out from here. Now, as we have discussed already about the concept of level in Taguchi design. So, if it is a two level problem, two level consideration or two level design planning, then the lower limit is set as nominal minus 1 standard of deviation and the maximum is nominal plus 1 standard deviation. That means nominal plus minus sigma and that is nominal plus sigma. However, if it is a case of say 3 level, then 3 level is something called max, min, mid and min, maximum and minimum, these two extremes, and the midpoint which we call here the nominal point, nominal value. Like say when we say a pipe, diameter of a pipe is 25 millimeter. Now, that is the nominal diameter. Does it mean that all pipes will be 25 millimeter? No, that is the nominal diameter, but then it may vary between say 25.5 to 24.5. So, that is the variation. So, nominal diameter, if I have to ask, I will say it is a 25 millimeter diameter pipe. Now, so here the formula for this, as you would find in the handbooks and other places of Taguchi etc., that the minimum is nominal minus standard deviation multiplied by square root of 3 by 2 and maximum is a nominal plus standard deviation into square root of 3 by 2. This have already been devised and it is universally accepted and it is used by the practitioners and everybody. So, and the mid value is nominal, as I said. So, this is the fundamental understanding. Here the important point is that in tolerance design, how we define which out of so many factors or components involved rather, all components are not equally responsible for the deviation or variation in the outcome. So, which are those on which the outcome depends is the first thing to be found out. So, which are those candidates on which we have to apply tolerance design in particular. There may be some other factors which has very limited effect or minimal effect. There we need not do anything because it is not contributing to the outcome. So, identification and controlling of those factors, identifying those factors are important and that is done through a concept called percent contribution, which is the key indicator with regard to which factors are the candidates for tolerance design exercise. That is those, it is written here also on bold on the right side you can find, that is those causing larger variation should undergo tighter control to effectively reduce total variation. So, now we have made the entire preamble, the background. Now, we will move on to a glimpse that I just in the beginning said analysis of variance, that is a calculation which perhaps you have already seen while doing parameter design or this ANOVA you will find plenty of books and materials. Learning ANOVA is not difficult. That means out of ANOVA is basically analysis of variance, that is the source of which affects the total variation how much, that is the analysis. And after see there is a total output and we are trying to explain the contribution of each factor. Suppose there are 5 factors. So, what is the extent that 5 factors are contributing to that, and when we are comparing that with the total variation, we find that there is a gap which is unexplained, where we cannot say that okay, we can say if there are 5 factors A, B, C, D, E, A's contribution is this, B's contribution is this, E's contribution is this and so on and so forth, but still the 100% is not complete, there is a small part which is still unexplained, that gap is called error. So, here we need those concepts and this treatment requires a statistical computation where there is sum of squares concept, and there is also a concept of, say, your mean sum of squares. So, so these are the things, that is error, as I said, is sum of square of total minus sum of square of individual factors, which are the components in this case. And mean of the squares for each factor is determined, and there is a concept called degrees of freedom. So, it is a statistical degrees of freedom, it has nothing to do with so called mechanical degrees of freedom, that it is having a 3 dimension, it is a statistical. So, any standard preliminary book on statistics you can consult, because see, these we are dealing from the product engineering perspective. So, I would imagine that your career would be in product engineering, that is the main thing, product design, product development, product engineering, and whatever, say, other materials, say statistics, because I hope you would appreciate that entire statistics, whatever is used here, from the very fundamental we cannot come up to this, because otherwise those will be different stream of lectures. So, one stream of lecture will be ANOVA, one stream of lecture will be on some other statistical methods. So, here I would suggest, in case it is I mean, there are so many materials available, you can go to any tutorial videos and you can learn it. And here therefore, there is a thing called significance test, which, as I said, which factor is important and becomes a candidate for tolerance design, not all factors. So, how significant is that it becomes a candidate? The significance is identified through a test called F test, Fisher's test. So, it is, that is why it is called F test, which is taken as the ratio of mean of the square for the factor divided by mean of the square of error. Error I have already told you what is it. So, this is a basic glimpse. I am not discussing the entire ANOVA process here. It is not possible also, because the course is on product engineering and not on statistics per se, but then whatever the statistical input required, I am introducing you to that, so that whenever you find it interesting, or more importantly when you find that you are needed to use it, then you can go to those and quickly learn it, because these are interesting and advanced methodologies for dealing with complex products. In fact, the more these things are done, one would find that without any major investment, by tweaking or by adjusting and controlling these values, would give much improved result, and therefore, the better quality at same or lesser price can be made available, which addresses also the affordability issue. So, that is why we have chosen to deal with it in this category, which is complex product and with affordability aspect. All right. So, now we proceed with that example. This example is self explanatory, and here we would deal with a throttle control mechanism. The throttle control mechanism is a kind of a product which is used in many places. It is used in snow blower, mist blower, lawn mower. So, there are several in an automotive, of course, there are throttle control, which actually controls the fuel, controls the air mixture, and therefore, the best outcome in terms of power generation and speed and all that happens, speed particularly. So, here such a throttle control mechanism, which is to operate that the user would maneuver, and there is some force required to adjust that lever to get that particular level of throttle. Like when you press the accelerator in your car, you apply certain pressure, a lever pressure. So, here also that lever pressure is applied, and according to the ergonomic convenience and the convenience of the best performance of the product, it is set at that 0.9 kg to 1.4 kg minimum and maximum load level would be the best, and that is the specification therefore. So, here in that product on the left you would find that this are the components, 7 components are used in all. In 7 components means 3 are washers, 2 are cone disc springs and lever and casing. So, in all there are 7 components which have been mentioned here. Washer within bracket 3 means 3 washers are used, cone disc spring within bracket 2 means 2 cone washers are used, C1 and C2, washer W1, W2, W3. So, W1, W2, W3, L, C and C1, C2 makes it 7. Now, here for each we have presented the nominal value, all are in millimeter on which is written on the top. So, here the idea is that the friction control should be such that when I fix it the the control, it stays at a particular point and does not move away so easily, but again it should not be too hard that when I intend to move I can also move it easily, or any the user can move it easily. So, the friction should be enough, but friction should not be too hard. You understand the challenge. So, therefore, there comes the tolerance design and the range. So, here the range is 0.9 kg to 1.4 kg. Now, here you see the here it is driven by the standard deviation as I said. So, the nominal values to start with, as it was felt that the standard deviation would be 0.125 in case of the washers and cone disc spring. However, it should be 0.25 for the other two, the lever and the casing. We will see if we choose this whether it satisfies the purpose. If it satisfies, fine. With this, if from our experiment we find that 0.9 to 1.4 kg is being made, that is fine, or else we have to adjust those values or the deviation values which actually is the control of tolerance. So, the deviation values are readjusted and the experiment is rerun to see whether now it is within the desired range or not. So, now we will proceed. So, here we have already given that those data, that is level 1 and level 2, that as you have seen that the, say for example, it has been done for all cases, the nominal value is 1 and the standard deviation is 0.125. So, if it is a plus nominal plus sigma on the maximum side and nominal minus sigma on the minimum side, if we are taking 2 level, then it would be 1 minus 0.125 as minimum and 1 plus 0.125 as maximum. Let us see. Here you see that the 1 minus 0.125, which is 0.875, is on the level 1 or the minimum one, or and the higher level is 1.125. So, similarly for it has been done for all components, the minimum and maximum, where for lever and casing it was 0.25. So, you can see the nominal value for lever was 19. So, 19 minus 0.25 is 18.75 and that is 19.25 on the higher side. Casing was 25. So, it is 24.75 on the lower side and 25.25 on the higher side. Similarly, for cone disc spring, etc. So, this is the minimum maximum values. Now, with this we run the experiment. The experiment here normally one experiment, experiment. So it is I said that there are 7 factors already in component and there are 2 levels. So it will be, as we discussed earlier, that it will be L8, the orthogonal array. L8 means there will be 8 treatment conditions, but the thing is here we could have just y1, but why we have taken y2? Because often it is found that single value may be erroneous. If 2 values are not close, then we can investigate if anything is gone wrong. So, though it is not mandatory to use 2 sets of data, 2 experimental runs, but it is always preferred that 2 experiments are carried out, so that if anything by any chance, I mean it is unlikely that 2 will go haywire at the same time, but probability is much less. That is why 2 are often considered, and that is what is recommended also. So, here you see that 2 sets of values are taken for the same 8 experiment, same means equal number of experiment techniques. So, 1 through 8, and the first set is giving the values as this based on the L8 or OA8 table, which we have discussed in the previous slide. So, I do not want you to be burdened with that again. You can always refer to an OA8 in the parameter design in the lecture number 30. And obviously, I have to do justice with time. So, I will not bring the old slides over and over again to explain that, but you can always check what is OA, and that will be a good exercise. This is way when you can just Google and find out what is L8, and you would see for yourself right away, right now in front of you in the in your laptop or computer or whatever, or mobile phone. This looks like a bit complicated, but do not you worry, it is not really so, because I have already explained all these things. The background theories are given. Here, as I said, that these are 3 washers W1, W2, W3, lever, casing. This by mistake is H, which should be C. We will make the corrections. Here it is casing. So, whatever these values are this, and so here what we find that the sum of square values based on the data already provided is 0.15, 0.13 and so on and so forth. Sum of squares etc., that you have already got that. Now, degrees of freedom 1 and total degrees of freedom, since these are 8 experiments and 2, that means total 16, and we know design of in the degrees of freedom would be that 16 minus 1, that is 15, which is at the bottom. So, total degrees of freedom is equal to 8 treatment into 2 replications and minus 1 is equal to 15. Then the mean standard deviation, or the called variant, this variance. So, the variance is the sum of square divided by the degrees of freedom, and you can see those values here. And the AF table, the calculation I have already discussed, and these are the values, and there is a table called AF table. Again, I do not want to burden with you this, you Google and find these AF tables at the different confidence levels. So, here what we see that except these 2 which are written in red have become significant. So, top 5 are significant. So, that for that the critical values, those which are above the critical values would be considered critical, and that would be known from the F table. If you consult F table and the MS error is equal to the SS error divided by degrees of freedom for error, we can find it out. So far so good. And now from here we come to the percent contribution. The percent contribution, if you see 0.215 here, and if we say that is the total and first one is 0.015. So, what is the percent contribution of washer 1 in this? So, it is 0.015 divided by 0.215 into 100, that is 7%. Similarly, for washer number 2 it is 6%, for washer number 3 it is 7%, whereas this lever and casing it is 41.82%, nearly 42, and that is nearly 36%, 35.78 to be precise. Rest are the values which are not high and they are not significant also, and the error percent contribution also is very small, that is 1.4. So, from here we find that percent contribution of these two components, this lever and casing, are maximum, and which constitutes more than 75% of the whole variation. Hence, we would try and see what we can do here, rather more precisely that we need to tighten the tolerance on these two components. Like it was 0.25 for each, now we have to reduce it, and therefore, these two, the red ones, it is called pooled, that we are pulling and merging it with the error, that means we are ignoring them and taking it as an error which does not affect us much. So, here this error degrees of freedom becomes 10 if we add these two red ones 1 and 1, and the total also get added, and so we are removing the spring aspect of the thing, and so we come to this new table. So, here we see the recalculate and we find that error has, by combination it has gone up from 1.4 to 2.4, but we now are better focused with the dimensions and see what is happening here, because we have merged that error term with the springs, fine, or rather the springs are merged with the error term. Here the equation is that the variance, which is the sum of square total by degrees of freedom total, and all these values are known to you already, which is 0.215 divided by 15, that is 0.0143. Standard deviation we know, which is the square root of the variance, that is 0.0143, which is expressed in kg. So, it is 0.12 kg. So, standard deviation now is 0.12 kg, but is 0.12 kg is good enough for our work? Question is, how much is good enough? Good enough is, our range is 0.5 kg, because we are saying it is operable between 0.9 and 1.4. So, 0.72 is higher when we are considering that 6 standard deviation, 6 standard deviation plus minus 3 sigma. So, 6 standard deviation is 0.12. So, if we are multiplying with 6, it becomes 0.72, which is higher than what is prescribed or what is desired target value. So, it will not work. So, what we do? We tighten the tolerance, as I just said. So, how do you tighten the tolerance? We make, say, put a factor of 1/4, 1/4. It is to some extent you can call it a trial and error method. So, we multiply those two only, rest all will remain same, those two only. We are reducing the their influence on the variance. So, we will see what the variance becomes, that for the just a minute, for which one it was? For the lever, for the lever it is 0.4182. So, 1/4 of 0.4182. Similarly, for the casing it is 1/4 into 0.3578, and the 2.4 the error is expressed as here because we are removing that percentage thing here. So, it is 0.024, and from this we find that the value of V t is equal to 0.006. Taking a square root of that would give us a standard deviation which is 0.0775 kg. Now, 6 standard deviation of that 0.0775 kg is 0.645 kg. Now, we will see if that works now. So, here you see that the first and last were the same, but in the middle two, the lever and casing, we are reducing the range, which was 18.75 to 19.25. We are reducing and we are increasing the lower level and reducing the higher level. So, what we are doing, we are tightening it. So, it instead of 18.75 it becomes 18.875 and 19.25 becomes 19.125, same is for casing thing. Now, what happens? We have to then with this new dimension we have to again run that experiment, as I said, again see whether it works. So, again the new experimental run is done and these are the values. So, it is iterative process. Now, how many times you do, no new information or knowledge you require, you only have to carry out the experiment. So, what happens? We do the exact calculation as we did earlier, same types of calculation, and we recalculate these values based on the modified dimension of the lever and the casing by changing physically, and now we are finding from the result what is the outcome. So, here the 5 factors or components are significant based on F test, and here we see exactly with the same calculation, and by pulling again that you see that here the S2 is minimal. So, S2 is merged with the error. So, 1 plus 8 becomes 9, S2 goes. So, rest all remains. That washer 1, washer 2, washer 3, lever, casing and spring 1. So, this is what it is. Now, now again, so the percentage contribution etcetera recalculated, which you see on the last column. Now, what happens? This would now require us to find out the standard deviation, which we have calculated, square root of the variance, which is 0.093 divided by 15, which we can see here total T sum of square is 0.093 by 15, and 6 standard deviation is therefore 0.474 kg. Now, we have to examine this is whether it is meeting the specified tolerance range, which is 0.5 kg, 1.4 minus 0.9. Now, we see that it is meeting it. 0.5 kg is the requirement and it is giving 0.474 kg. Therefore, these tolerance values are acceptable. So, here through these steps you know how to set the tolerance for components, so that outcome is influenced in a way that it meets the desired or target values. In conclusion, I would like to point out that this tolerance has been explained with an example. The objective is to familiarize with the design methodology, which is important from the perspective of product engineering and is different from the conventional specification limit based analysis, and addresses the effect of variation from various sources and reduces their effects on the product performance variation. But the video tutorial material is scantily available. I repeat, this procedural steps therefore is in place, that have been explicated with an example. It is anticipated to be an useful input for the requirements in practice and for the students and for developing their product engineering skills, particularly for complex products. Hope you will take interest and go through some of these statistical techniques, easy to learn, and you will certainly use it in certain applications of yours. Thank you. Before I close, I would like to mention the reference which is here, and finally, I thank you for attending this lecture. I am sure you would be it will help you and you would be using it in your work. Thank you once again.